Okay, good evening, class. Um, we are continuing a discussion on neural networks. We started with the biological motivation for neural networks. And from then onwards, we went to what are the kinds of functions that are used in building neural networks, the activation functions, and also the kind of functions we are trying to learn for regression or binary classification or multi-class classification. So those are the kinds of functions we're trying to compute, and we use activation functions, which can be of various sorts, like sigmoid and all that. And after that, we went on to how to train these networks, which have parameters that are built into. These are all weights associated with all the links in the network, and these, although the function at each level is a linear function, but a linear function of those parameters. So these are activations are linear functions of the inputs, which needs parameters. We said W transpose X, right? So W are the weights, those are the parameters. And those together get added up at each node, and then we apply an activation function to that to produce the output between 0 and 1 or -1 and 1, what have you. And so how do we learn those weights is through an idea called backpropagation. And in backpropagation, it's an efficient algorithm for determining the weights. It's all based on calculus, where we apply the chain rule of calculus to multiply the derivatives at each link. That's all it is. You multiply, one derivative with the next derivative, the next derivative, the next derivative, to be able to get the derivative of the first input of the input with respect to the output. So, and then we got to keep track of it, and we got to sum up things that are coming from the same place and so on. So we use computational graphs for doing that. So that's the kind of thing we've talked about so far. So today we move to another topic within neural networks, and this is called regularization. We've encountered regularization earlier on, even with logistic regression, even with linear regression. We talked about regularization. Now we'll talk about it in the context of neural networks. And uh, there are many types of regularization. It's a very active topic of research. And some are very well known, like norm penalties is a method of regularization. And um, and what else? There are like L1 norm, L2 norm, and so on, which try to keep the length of the weight vector small. It's called weight decay. And there are other methods of regularization uh, that some of them are related. And there is data augmentation is a method of regularization. Instead of using the standard data set you've got, to somehow expand the data set by creating distorted versions of the input, that creates a variation. One thing I must mention, an intuitive idea, what is regularization? The answer could be it is unlearning. Unlearning means not to learn too much, right? So it says try and keep a open mind, and don't learn everything literally. And that is there to help you learn, but you got to be able to generalize beyond the rote learning. That's what regularization is. So you would like to generalize to data that you have not seen before. That is the power of learning. So this is what we do, and these are all intuition built into this regularization. Keeping the weight vector small. If you make it very large, it means it's a very specific point somewhere far away that's fitting too well to the data. So we will look one more look at L1, L2 norm penalty, which is also called weight decay, because we're trying to decay it towards the origin or zero. We will also look at data augmentation, And we will look at a specific way of data augmentation is to rotate and translate the data in 2 dimensions to create a better set. And then we will argue that this method of rotating and translating and then regularizing based on that is equivalent to a Bayesian approach to the problem of regularization. Bayesian approach is a wonderful approach, theoretically wonderful, I should say, practically not that much used, but it's theoretically it's a beautiful approach, which says let us build in some prior distributions on the weights rather than assume that the job is to figure out the weights from scratch. Can we somehow assume a probability distribution of the kinds of values that the that it takes, and and then say, okay, can we improve upon it? So we say this is a problem. Learning the weights is not a problem of fixing the exact number, but learning a sharper distribution which tells you, what value is most likely and what other values are less likely and so on. Hopefully it's sharp in the sense one value is getting a very, very high probability. So we will look at this data augmentation by transformations as equivalent to a Bayesian formulation. Uh, and there is so much more to go beyond that in regularization, other than data augmentation and transformation. Maybe that's all we'll be able to do today. We'll have to keep a couple of classes for this topic of regularization. um, and we'll see what all there is as we encounter them. Oh, there is one more method that I have for this series today, if we can get to it, is what is called as tangent distance, which is also related to the idea of transformations, is to look at these inputs as points in a space, in this multidimensional input space, where if we subject them to a transformation, a slight transformation you make on the data point is also going to move a little bit. So in a way, we argue that a whole series of transformations will trace a manifold in data space. Manifold is some kind of a space, some kind of a smooth surface in this high dimensional space. We're going one point to the next point. You can go this way, that way along the surface, and along the surface known as the manifold. And and then we define something called, instead of measuring distance between points, we can measure distance between points and the manifold, the different definition, which involves drawing a tangent to the manifold. If I give you a manifold and I'm saying I'm at this point here, then you draw a tangent plane to it, and you say use the tangent plane to figure out how far are you from the manifold and so on. So all of it, all kinds of interesting mathematics, geometry come into play. All right, let me share my slides now. I have also posted it. No, did I? I haven't posted it on UB Learns, which I will do that after class today. So let me share screen now. Okay, there we are, to regularization in neural networks. Okay, this is the topic, regularization in neural networks. All right, so the topics here in neural network regularization. First, we begin with definition of regularization. I've already indicated to you what it is. It is unlearning. All right, that's what the definition is. or to generalize it. It means generalization to unseen data. And so, what are the methods of regularization? Limiting capacity is one of them, number of hidden units in the network. If you have a very high capacity, it means it can learn a lot and it's got too many parameters and it fits exactly. Um, Actually, that brings up an interesting issue. Should you put a lot of hidden units into your network or should you put less, saying don't learn too much? Actually, the answer to that question is uh, use a higher capacity. Use more nodes, but use a good method of regularization along with it, such as non-penalty L2 and L1 regularization. You could use, which which is a method of regularize. As long as you have another way of regularizing other than limiting the hidden number of units, the performance is better. Okay, so it has to have some capability to learn, and then use a good regularizer. Non-penalties are L2 and L1 regularization. We can argue that these are equivalent to some Gaussian priors. So we'll see what that connection is. What is the Bayesian connection to regularization? See, the term Bayesian comes in wherever you use prior knowledge, then it becomes Bayesian. And when you are saying, I'm going to use regularization of the penalty, non-penalty, aren't you using prior knowledge? Yes, we are. So what kind of prior knowledge are we using by using L2 norm or L1 norm? Well, you are assuming some kind of a Gaussian around the weights is what the answer is. Okay, now then we have data set augmentation, which means creating more data to feed to the network. Early stopping is one of them, where we say don't keep training. You stop at a point where you have not minimized the error completely. You're stopping, and the stopping, of course, is based on some kind of a validation set, which says performance is getting worse now. So we stop at that point. That's early stopping. And there is all kinds of arguments as to why that is mathematically justified. And then the last of these topics is the tangent distance or tangent propagation, which I just mentioned. So definition of regularization. So generalization error should be minimized. Performance on inputs not previously seen. It's also called sometimes the test error. And regularization is any modification to a learning algorithm to reduce its generalization error, but not its training error. Right? So there's an example given over here where we have the error keeps going down and down and down with the training set, which is the blue dots here. And but we see that on some kind of a validation set, the error kind of keeps going down. Then after a certain point, it starts creeping upwards. And so we say, look, the generalization error is going up. This is the test set. This is not seen, unseen set, right? That's what the validation set here is. And so we say we should stop here. This is the early stopping part here. And so we are not necessarily reducing the test training error to zero, but we are not reduce we are reducing the generalization error. Instead of going up over here, we're bringing it down. And this gap between the training and test performance is referred to as a generalization gap. And we can talk about this red line here, which says this is the underfitting zone, which means we could have done better. Underfitting means we haven't reached optimal performance. Overfitting says you have fitted too well. So the optimal capacity we say is over here. So you need to model capacity should be limited either by maybe like number of hidden units can determine the capacity, and says if you add more and more degrees of freedom, it will fit much better. But you have to worry about this generalization gap here. So goals of regularization are to encode prior knowledge, express preference for a simpler model, and need to make underdetermined problem determined. All right. So the problem These are all some of the goals where you are trying to figure out where you have many degrees of parameters and may not have enough data, and you need to fit a solution to it, which is the problem of underdetermined problem, make it determined, and express preference for a simpler model. That particular philosophical idea of choosing a simpler model over a complex model is known as Occam's razor. It's an old philosophical principle which says when you're trying to find an explanation for something, don't use a very complicated explanation and use as simple an explanation as possible. That's probably more likely to be correct. So the need for regularization is to prevent overfitting, Occam's razor, which I just mentioned. And the Bayesian point of view, regularization corresponds to prior distributions over model parameters. Best model means what you're going to use to solve the problem. I gave an example of a feed-forward network of US elections. And in a way, it's a model. This model takes as input votes, creates electoral votes, and from electoral votes makes it. In a way, this whole thing is a model. That model can be changed, saying, okay, you want to go from these inputs to the output? There are other ways of doing it too. So this is you can think of the electoral college system as a particular model of finding the output based on the inputs. And you can argue whether it's good or not, right? All right, now, um, best fitting model is a large model that has been regularized appropriately. So use a large model with large capacity, but it has been regularized. And we review several strategies for how to create such a large, deep regularized model. Limiting number of hidden units, number of input output unit determined by dimensions, number of hidden units. M is a free parameter adjusted to get best predictive performance. Yeah, you can think of how do I select how many hidden units do I need? Well, you could use that graph we just saw. You keep on increasing the number of hidden units and you find the error is going down and down and down. And maybe at some point, as you are adding more and more hidden units, it is overfitting. And so you may want to say, well, at this point, I should restrict. All right. So in a way that can be used as a way of determining this hyperparameter, number of hidden units. Possible approach is to get maximum likelihood estimate M for balance between underfitting and overfitting. And that's interesting that it is possible to get some kind of an estimate for the number of units itself is a mathematical formulation. So effective number of hidden units is being talked about here. Sinusoidal regression problem. A neural network can be used to solve a regression problem. A two-layer network trained on 10 data points. So the hidden units and the input units and the hidden units. And let's say we have 10 data points like this. And this is showing the output m equal to 1, what kind of fit is getting, m equal to 2, what kind of fitting it's getting, and m equal to 10. This is a number of hidden units, 1, 3, and 10 hidden units. And minimizing sum squared error function using a particular gradient descent called conjugate gradient descent. And so you might get this kind of a behavior, the same 10 data points. M equal to 1 is an underfit. M equal to 3 is just a nice fit, sinusoid. M equal to 10 is overfit, which is kind of running through all the points exactly. We're getting a very, very awkward shape, which is not representative of the true data, but it's fitting every data point in the training set. So, so this issue is a little bit nebulous, but there are some guidelines like this for choosing a number of hidden units. And this is a slide about validation set to fixed number of hidden units, and it gets you a little example, sum of squared error, test error, number of hidden units, and so on. Anyway, just is an example of what I just discussed, that you could use the capacity could be determined by the error, or test error in this case. Okay, now so let's go on to the first method of regularization other than the number of units. This is the norm penalty. We say the loss function you're trying to minimize, E of W, is replaced by E of W plus lambda over to W transpose W, and call the new loss function as E tilde of W. So this is called the weight decay regularizer. So in a two-layer neural network, uh, we can think of, for example, the loss function. So what is EFW was stated as the loss function? What is this loss function? So the regularized loss function is shown here as J regularized. This is the cross entropy cost. It's we've seen this before. It comes about when we start with the Bernoulli distribution. We can show that it's cross entropy. We've done that a little bit earlier on. Now it has been stated in terms of different variables here, the inputs and the parameters, that kind of a thing. And this is the cross entropy cost over here. And this is the L2 regularization cost, which shows the weights. It's a two-layer network with uh, kj. It is summing over all the weights in the network in terms of the input and the hidden layer and the output, all the weights that's involved, and there's a lambda here that is multiplying that. And what is this m here? M is based on the number of samples in the data set. So you're doing, and of course this M could also be a mini batch, right? It could be a small number of data points, or it could be all the data points. They chose M particular rather than N. N is usually number of data points you got. M is some subset of the N, which is the mini batch you're training on. So you're summing over all of this, or all the individual samples. and so anyway, this is the expression that has to be minimized by the neural network. So the weight decay is the name is due to the following: Wt plus 1 equal to Wt minus alpha uh, derivative of J, and this is how it is. It's being expressed with a lambda going with the weight also, because of the form we just saw um, of the cross entropy. And to prevent overwriting, every time we update weight W with gradient delta J, or nabla J, I should say, in respect to W, we also subtract from it lambda W. This gives the weights a tendency to decay towards zero, and hence the name. So anyway, that regularization we know, so it's nothing new about this. Some form of it is here. Effect of neural network regularization. So it's a classification problem we are doing, right? It's red and blue. We just talked about presidential election, and we are trying to determine whether any new input is red or blue. And if you model without regularization, can be pretty complicated here. Pretty complicated. The red island over here, the blue island over here, and all that. And if you use a model with L2 regularization, if you use that additional term, that is going to take care of all these fine, you don't want this to be so fine-tuned. This is overfitting here, overfitting. This is maybe the data got generated by two Gaussians or something, in which case, if there were two Gaussians, the same covariance matrix, the boundary would be actually absolutely linear. This seems to be close to linear here. And that effect has been obtained by having a good regularizer built into that. So that's the effect of the regularizer over a unregularized solution to the problem. Okay, we move on to a data augmentation. That is, what should we do when we don't have enough data? This is actually a real data of a human heart. All right. So It has a human heart. Human heart. I think it's a cross section of the human heart. There are two regions here. They're called the ventricles, right? There's the left ventricle and the right ventricle in the human heart. And apparently, one of these ventricles, the cross section is a nice spherical shape to it. One of them is always nice. The other one is a crescent shape, which has got much variability. The is a right ventricle. The left ventricle is like this. So detecting left ventricles is easy. Detecting right ventricles is harder because the shape keeps varying. And so this task they were doing was a machine learning method to figure out where is the right ventricle. Give me the border of the right ventricle, and they do that for every moment of time. So you're saying because it's going to be the heart is beating, so the heart size becomes larger and smaller, or this cross section size becomes larger and smaller, and they measure the blood output from the heart by how much this is varying, how much is the right ventricle varying from image to image. But in each cross section, they need to figure out what is the area of the right ventricle. And so in order for a machine learning program to automatically identify the right ventricle, a cardiologist, a human doctor, would have to sit and label out and say, hey, that is the ventricle, right ventricle. And these right ventricle shapes are not very distinct sometimes, and the shapes vary widely, so on. And you only have a few examples because having a human annotator annotate it like that is expensive in a time of a cardiologist. And how many samples can you create with labeled examples? So one approach is to create artificial data. They took the same image and you rotated it out several times like this. So use all of these images to train it. They only have one image, but you're creating a larger data set. Apply transformations on the fly so the network sees new random transformations during each epoch. So anyway, this is called data augmentation. Oh, I've been going backwards rather than forwards. All right. So here is invariance to transformation. You may have simple weight decay, a certain shortcoming, invariance to scaling. They or same building, different views and scale. This building and this building are the same, taken at a slightly different angle. So do we train on various, varieties of transformations, or are there better solutions is the question. So we'll first take a look at building invariance into a neural network for rotation. First of all, we need to understand this is just a linear transform rotation in the two-dimensional plane. It's not a three-dimensional rotation like the building we saw. It was 3D. Whereas on the plane, we saw the heart image, which was just being rotated on the plane. So if you have every point xy on your object of interest is transformed to a new value. The new value is given by transformation. Ax plus by is first value, cx plus dy is the second value. We can show that the transformation of xy is multiplying the xy value, the 2 points, the value of the two values being multiplied by a matrix ABCD. And we say T of x now is a vector with these two values, can be written as A of x, where A is this particular matrix. So if you choose that matrix to be minus 2, 0, 0, minus 2, and you multiply the input points here, it turns out that these are unit length here that becomes twice the size because we're multiplying by minus 2 and minus 2 here. And there are two zeros here. So these points, these blue, yellow, red, and green points get transformed like this, green. So it's going to rotate. It's going to rotate it as well as comes on the other side of the x-axis. If you multiply this by minus 1, 1, 3, it is creating some kind of a, squeezed version of it like this here. And what about here? When a equal to minus 1, minus 1, minus 1, 1, that takes these four values here and creates this kind of a diamond out of it. These are all transformations. And this last one is a three-dimensional kind of rotation of a three-dimensional object. You have x, y, and z here. You have x, y, and z. That's being transformed by a three-dimensional matrix to create a distorted cube over here. This is a cube that's being distorted. So these are what are called linear transformation. So then we'll ask ourselves the question, what does it take for a neural network to perform the same for the original object or its transformed object, or how do we deal with it? How do we deal with transformations? So let's work with a two-layer network, sometimes referred to as a multi-layer perceptron. And so we say a set of inputs xi and outputs yk, and activations of hidden units in the first layer have this form: zj equal to h of w ji xi plus wj naught. So these are the hidden units. And activations of the output units are at the, this is the zj, I guess the yk, right? The yk takes whatever z as input in a similar way. So if you perform a linear transformation of the input data, xi is replaced by axi plus b. When mapping performed on the network is unchanged by making corresponding linear transformation of the weights and biases. So the weight should change like this. The weight should change like that, so that the output is not changed. So desirable invariance, the regularizer. Suppose we train two different networks. First network trained using original data. Second network input or target variables are transformed by one of the linear transformations. Okay, consistency requires that we should obtain equivalent networks that differ only by linear transformations of the weights. And now we argue that simple weight decay fails that invariance. So if we train the network like this, if you rotate the object, you're not going to get the same output, right? So what do we have to do to build in that kind of invariance into the network? And this says such a regularizer is lambda 1 over 2 w belong to 1 w squared, lambda 2 over 2 w belongs to w2 w squared. So what it is saying is use separate regularizers for the first layer and the second layer. And this regularizer remains unchanged under the weight transformation, provided the parameters are rescaled. Okay, there's something more needed here. We have seen before that weight, okay, so this is saying it's possible to do that, to build in invariance by handling the weights regularization judiciously and not using a single weight for each of the, or single lambda, right? This is the hyperparameter that's being used. All right, we've seen before that weight decay is equivalent to a Gaussian prior. So what is the equivalent prior to this? So this is making a side trip here into the Bayesian approach, Bayesian linear regression. So where we are trying to get an output T given a set of values X and set of weights beta, and we define a probability distribution as the product of normal distributions. This is the regression problem. This is not logistic regression, it's linear regression. We're trying to learn the weights and we say, well, can we have a prior on the weights? W given some hyperparameters, it's a normal distribution of these. So you see what it is this is the probability distribution of the parameters or two weights, W0 and W1. A Gaussian prior is being plotted here and all equal circles, the constant same variance in both directions. And think of a normal distribution hill sitting on top of it. These colors correspond to contours of similar density. And so if you use Bayesian linear regression, the output is this distribution, the prior distribution is like this. And the posterior, based on the set of weights on the weights given the samples, can be written in this way. And the log of this posterior distribution of the weights, we go from prior distribution to posterior distribution by using the likelihood times the prior. Usually in the Bayesian approach, you say posterior is equal to likelihood times the prior. And the log of the posterior is this, and the maximization of the posterior is equivalent to weight decay. Oh, wow. What all this exercise here is to argue that this weight decay based on L2 norm, it didn't come magically from somewhere. It can be derived as assuming a prior distribution over the weights with an addition of a quadratic regularization term, with particularly lambda is equal to alpha or beta. This has got something to do with the hyperparameters, that alpha is the parameter used to define the prior Gaussian, and beta is the noise parameter that occurs in the noise model used for regression. Anyway, there's a little beautiful piece of discovery here, that the L2 norm emerges from a Bayesian formulation. So we are using some prior knowledge about the weights. When you're saying, hey, use the length of the weight vector, it sounds really strange when you first encounter it. Why are you doing length of the weight vector? And you call it weight decay, all right, but why is that so good? Well, here is an argument for that. It's a very nice argument. Um, Equivalent prior for neural network, it corresponds, yeah, what is the prior that is equivalent? We just saw this w squared, lambda 1, lambda 2. And it says it corresponds to a prior of this form. This is for the transformation of rotation or linear transformation. And it says that is equivalent to assuming a prior. All right, there is some graphs here which I'll skip, which shows what happens input-output relationship for different settings of the hyperparameters and all that. It's a lot of detail. It's a nice paper that's been abstracted here. Okay, we saw about early stopping is to stop at the point where the validation set error starts to increase, and we say here is validation error is increasing, so we stop at this point, whereas the training error is getting lower and lower. And we can interpret the early stopping as what's happening in weight space. This is W1, W2 weight space. And this red ellipse is a contour of constant density of your loss function. The loss function can be thought of as imposed on this plane here. And we are assuming this is a convex optimization, that there's only one minima or maxima. We are heading towards this WML. This is the value of the setting for W1 and W2 where this loss function is minimum. That's where we want. And we start, let's say we started it from 0, and then we are approaching like that. But early stopping says don't go all the way to approach the 0, the minimum here. Maybe we stop right here at W tilde. And W tilde is again somewhat analogous to weight decay. And we are not bringing it down to the point here that is closest to the origin. And so we are stopping somewhere in between the two. Right? All right, so these invariances, we go on how it is necessary in classification. We need invariances such as we need to be classifying it correctly, irrespective of position in the image, translation, size. And anyway, these occur all over the place. And so there are, we just saw a few approaches for invariance already. And of course, we just saw training set can be augmented. Regularization term to error function, that is something we just saw. And we'll see a little bit more in this approach of tangent. So one more approach is, let's say we were doing handwritten digit recognition. Here is a scanned image of a 6. And we are doing random displacements, derivative x, derivative y at each pixel, then smooth by convolution. And synthetically warp each handwritten digit before presentation to the model. So these are being added to this to create slight rotation, and then you create images like this. These are all warped images, random displacements that's being performed on these to get new images. These rotated versions can be thought of as uh, creating a manifold in space, in the input space. And manifolds can be traced by making small transformations. For example, here is the face of somebody, and the face is being rotated from left to right as you go from left to right here. And as you go from top to bottom, the face is looking upwards and looking downwards. So you have this face, for example, looking downwards being rotated here, and this is looking upwards being rotated here. And so you got all these in-betweens here. So all of these form some kind of a manifold in the input space that you have. So this tangent approach is uh, based on the manifolds. Let's say we have an input S here, like this is the face. And as we move the face and transform it slightly, we are moving. Let's say the transformation is only one type of transformation. So we're only moving along this line rather than in a surface, right? So that is how the object is moving. And we would like to recognize this person irrespective of looking up, looking down, looking left. How many of those images can we train it on? So we want to be smarter about it rather than trying to do every possible transformation to that face. So these tangent approaches say, let's say we were using a very simple classifier which simply says, here's an input P, and we want to classify, we want to find the distance to the point S of that person's face, as opposed to distance to some other person's manifold. Every face you can think of as a different manifold. And we can say any input one, we can say whose face is it similar to? Instead of measuring the usual Euclidean distance between these 2 points, in some set of features you have, we ought to be measuring the distance between that point and a distance to the manifold, closest point in the manifold. Not that point, but check out, because it's the same one coming over here. So maybe the closest point is this. It is this version of the face. It's closest to this. But computing the manifold and finding the distance is a complicated matter. And a more reasonable solution is what's called tangent distance, which says, if you have this manifold and you got this one sample of that face, instead of trying to compute the distance to the manifold, draw a tangent at that point and then measure the distance to the tangent. And so that becomes the distance of this unknown person and this person S here. And say that measures not the standard Euclidean distance, but a tangent distance to that point, which takes into account how the surface is changing. The tangent would have been some other way. It's kind of telling you that, okay, it's kind of turning downwards here. That's why this thing is also going downwards here. So there are 3 types of distances shown here. And this one is showing a face here which is being made enlarged, scaling and rotation. So those are other transformations. What if the image is scaled, made larger and larger and larger, and rotated and rotated and rotated like that, right? So you have now two dimensions in the transformation, scale and rotation. So here also we're showing scale and rotation. And what we're doing here is plotting the distance, let's say, between the origin and the particular image. And as you change the scale and rotation, that distance keeps changing. And there are three surfaces shown here. This dark gray here, and then this slightly lighter gray here, and then the lightest gray on top. The lightest gray on top is the tangent distance, and then below that is the manifold distance, and this lowest one is the Euclidean distance between the origin and the point. And so you get all these surfaces. So this says uh, when you do these rotations, the point is moving along like this. Um, and so I guess this is a space of transformation as opposed to the space data space as such. And so anyway, this is the kind of thing that is computed. As you can imagine, the computation is pretty complicated. So they use a method called tangent propagation, which says, supposing you had two inputs, x1 and x2, and we are applying a transformation psi, which makes the data move along this manifold M. Here is a point xn on that manifold, nth point, data point. And we are computing the tangent. We just saw what the tangent looks like, the tangent. So this idea, it was mathematically stated here, is tau n, is this tangent, is the derivative with respect to psi, this transformation, of an input S whose parameters are this point xn and the transformation psi. So this is the value of the tangent at psi equal to 0. That's at that point here. So using that idea, under transformation input network, the network output will change. The derivative of output k with respect to psi is given by d by k of d psi. This shows the j, which is the criterion function, loss function, and the transformation we just talked about. And this derivative of output k with respect to psi is given by this, and the result is used to modify the standard error function. So we're back to the loss function of the neural network regularizer. It's got e plus lambda omega. What is this omega? Omega is in terms of this derivative we just saw, and it's being summed over the samples n, right? And the dimensions, and this is the dimensions here of the data. So that's coming into play here. Anyway, it's a bit complicated, but you see the idea of dealing with data that is transforming, and the neural network somehow has to be invariant, that it should perform as well on the faces, for example. One way of doing it is train it on all the rotated versions. That seems like a brute force approach. This is a most nuanced approach to that problem. Anyway, this talks about how do you compute those derivatives and so on. And you take tangent vector corresponding to a clockwise rotation, and then you're computing the derivative tangent vector tau. So for this the tangent vector looks like that, and you add the tangent vector to this, you get this image. This is the original image. This is a tangent vector. Add the two, you get this image, which is equivalent to rotating it by a little bit. And if you simply rotated the image, you get this, which is kind of close. Anyway, it gives you a sense of the tangent idea. So these approaches are equivalent. And summer squared error function can be shown to be equivalent to tangent propagation. So these are all related methods. That's what's fascinating about it. It's not just arbitrary tricks. Expanding the training set is closely related to tangent propagation. Okay, that's about what I have for today. We've got a lot more to do on regularization. I'm going to stop at this point. And are there any questions for today's lecture? Okay, so Meher, are you ready to take over?
Yes, Professor.